Bismillahirrahmanirrahim. So today we'll start the transport layer for wireless mesh networks. So the transport layer in wireless mesh networks or in any ad hoc network is designed to provide an end-to-end application communication. So you have an application running on one end host, needs to communicate with another application running on another end host. So they need to communicate either in unidirectional or bidirectional way, which means that you have to have segments or data going back and forth. So of course, when it comes to transport layer, the most common protocol is what? TCP, Transport Control Protocol. And I know the answer for the question that's coming. So if I ask you, what do you know about TCP, or do you actually know about TCP, then the answer may be, at least for some of you, no. So, okay. So, so I thought we'll start with a blank slide just to explain the concept of TCP. Okay. So, so basically, if you have an endpoint application A needs to communicate with another endpoint B. So the way TCP works is that A sends one segment of data, okay, and then for each segment, B needs to acknowledge. So this is the segment. So this is segment 0, for example. It has a length, let's say 100 bytes, and it has a sequence 0, and so on, right? So this is an acknowledgement. The acknowledgement, the acknowledgement will be 101 to indicate that I received 100 bytes correctly. Please send me the next one. That's what the acknowledgement usually means. So, TCP provides what we call flow control, congestion control. It provides reliability. All of these features as one package. So either take it or leave it. It's not like so flow control talks about the fact that A can send multiple segments all at once, okay, without having to wait for acknowledgement. So this way, I can just send multiple segments and not having to wait, because if I wait for every time, then I will lose the opportunity here. And I keep waiting for a long time, not utilizing the channel, which is bad. So flow control allows me through what they call like window mechanism that I can keep sending the segments. Once I receive acknowledgement, I can slide the window and keep sending. So receiving positive acknowledgement means that I can slide the window and keep sending more segments. Otherwise, if I send like 4 or 5 segments and then I do not receive any acknowledgement, then I have to wait. This is basically flow control. Flow control prevents A from overwhelming B, which means that the more acknowledgement B sends, the more it tells A that I'm coping with the scope, you can send me more. That's what it means. If B cannot send acknowledgement, then A will take that as, B is not coping with the speed, so let me reduce it down a little bit. Okay? The problem with the flow control is that TCP, what it does is that TCP uses like the gradual increase of rate and multiplicative decrease, which means that if I don't receive the acknowledgement for a specific period of time, which is the timeout, then this is an indication for me that there is a serious problem happening either with the receiver or with the network. So the response for me is that I have to drop down the rate of transmission. So instead of sending like 4 different or 5 different segments, I'll send 2 and wait. And then when I receive the acknowledgement, I'll send 2 more. So the amount of segments that I send without having to wait for acknowledgement varies depending on the actual number of acknowledgement that I receive. So if A keeps sending segments and there is a congestion in the network, like there is one router here that's congested, chances are this acknowledgement will not arrive on time, and I will have to I will time out. If I time out, this means that this gives me 2 pieces of information. One is that there is a congestion on the network. 2, B did not receive the segment that I sent, so I will have to retransmit it. Okay? So this is what we call, if a congestion happens in the network, then we call this congestion control. Congestion control means that there is a block or there is an overload inside the network that prevents the segments from going through smoothly. In which case, I have to slow down the rate. I detect the congestion through multiple ways. I can detect the congestion simply by not receiving this acknowledgement on time, which means that there was a significant delay in the segment and I did not receive this acknowledgement on time. In that case, this is an indication for me that there is a congestion in the network. Okay? Or there is another way of indicating congestion control through what we call a explicit congestion notification. And that happens by the router. So the router that's congested will send back this ECN control segment or control packet to the source. That's why it's called explicit congestion notification.
Because this is on the transport layer?
Yeah, this is all in the transport layer.
The application layer cannot detect this.
application layer is everything happens underneath. The application layer doesn't even feel it. The application layer sends something and TCP will be responsible for reliably delivering this packet to the other application on the other side. Okay, so if there is any problem, whether it's congested or not congested in that case, overwhelmed application on the other side, the overwhelmed application will inform the source implicitly by not sending the acknowledgement on time. Okay, so
And through the transport layer.
yeah, everything is through the transport layer. Now, here we're talking about transport layer. Okay. If the network is congested, then I can sort of get some indication about this in 2 ways. Actually, there are multiple ways, but the 2 common ways are, again, delayed acknowledgement, in which case I will get the indication that the network is congested, or the receiver is congested. And in all cases, the reaction for me is the same. I have to drop the rate, or using explicit congestion notification. Okay. So the only thing left is that TCP calculates this timeout iteratively. So this timeout gets estimated dynamically during the transmission. How? Basically, A will calculate the time that the segment goes all the way to B and come back. So whenever it receives an acknowledgement, it calculates what we call a round trip time. We talked about that last time, right? Round trip time. So the round trip time is the time that the segment takes to go back and forth. Okay? So what is the timeout? The timeout is based on the moving average value of this round trip time. Moving average means that this is the instantaneous value of round trip time, and this is the average round trip time through multiple iterations. This is the average. So we take the weighted average between the two. So we multiply this by alpha, we multiply this by 1 minus alpha, and then get the summation. And this will be the new value for the average round trip time. Then we add some factor of safety to that, and we use this as a time. So this is a small crash overview about TCP. So this is how TCP provides flow control, congestion control, and calculates the timeout. So now, what is the problem now? The problem. Sure.
The safety value, where do you extract? Like alpha?
No. The safety value is that the safety value is based on هو the timeout equals the average of round trip time plus some factor of safety. They call it, I can't remember exactly, but 4 times deviation factor. This deviation factor is because if you see the instantaneous measurements of the round trip time, it may go like this. This is the instantaneous value, right? So if I take the average, this is the average. If I base my calculation based only on the average, then all these states will perform very badly, because when the round trip time increases to these peaks, then the timeout will be smaller than what it should. What is the effect of this?
More retransmission. More retransmission.
More retransmission, because the acknowledgement will be slow enough that I will time out before the acknowledgement comes. For the effect here will be that the acknowledgement will be slower than the timeout. So we'll keep timing out prematurely in these cases.
Yeah. So you're raising the bar a little bit.
So yes, so we need to raise the bar a little bit. So what happens? So what happens is that what they do is that magic, huh? Okay. So what we will do is that we will calculate the difference between the instantaneous value and the average value every time. And then multiply this by a factor of 4, I think, or something like this.
So it changes?
It changes. Of course.
For every
of course.
round trip?
Yes.
Oh.
Yeah. And then the round trip time or the timeout will be the average round trip time plus 4 times the deviation factor. The deviation factor is the difference between, is the average difference between the instantaneous value and the average value of round trip time. So this deviation factor is even moving average as well. So we calculate it based on, we subtract the peak value from the average. And this will be the instantaneous deviation factor. And then we calculate the moving average of this deviation factor. And we multiply it by 4, we add it to the round trip time, and this will be the time multiple. Again, this is based on some experimental investigation, and this is what they found to be working with a good performance. Okay, so this is an introduction about TCP. So the problem here is that TCP was designed initially for wired network, for mainly Ethernet, to provide this reliability, congestion control, flow control, and so on. It's one package. Either take it or leave it. There's no customization for, I need flow control, but I don't need congestion control, or I need flow control, but I don't need reliability that much. So even for wired networks, TCP was not the best choice, for example, for applications like video. So you rarely find video over TCP. Why? Because video does not require reliability that much. So if you lose one packet of video, that's not a big deal. This will reflect as, like some pixels being dropped on the, you won't even feel it. But on the other side, on-time delivery is very critical for video, right? Because if you don't deliver the packets on time, then this will reflect as a very bad quality of experience on the user. Why? You're watching a game and there is, somebody says goal and then you're not seeing anything because the packets are delayed. That's not acceptable. I much rather prefer to drop these packets but deliver the other packets on time rather than just delaying all the packets and assure 100% reliability. So TCP performs very badly with video. But our problem is not video now. Our problem is over mesh network. So what is the problem of TCP when it comes to wireless mesh networks? Okay, so that's what we need to talk about. So this was like a very quick introduction. So the transport layer in wireless mesh network is divided into two things. First, we'll take TCP, we'll try to take TCP and see what's wrong with it. What makes TCP perform badly in wireless mesh network, if any? Okay, and try to amend TCP or create some variations of TCP that will perform better when it comes to wireless mesh network. So that's the first approach. So this is what we call an evolutionary approach. You take whatever is there, enhance it to work for your purpose. Or a revolutionary approach is to design a whole new protocol for transport layer, for wireless mesh networks. Okay. So first, what makes TCP behave or perform very badly in wireless mesh network? Well, the first problem with TCP is what we call non-congestion packet loss. And what that means is that any packet loss that happens with TCP will interpret this as what? As congestion. And what is the ultimate reaction to this? What is the only reaction to this? Slow down, and slow down exponentially. So what TCP does is that in normal operation, it keeps increasing the rate linearly like this. Once it finds a packet loss, drop down. And then if the packet loss stop, then it knows that it's going fine. Then increase gradually. And then if there is any packet loss, it drops completely down, and then it gradually. So this is what we call gradual increase, multiplicative decrease. So that's how TCP works in terms of congestion control. The problem now is that for wireless mesh networks in general, the packet loss may not be because of congestion, right? The packet loss may be due to an instantaneous channel variation due to any random effects, like deep fading in the channel, or like someone is walking by. So that may affect the channel instantaneously. But this is not congestion. Congestion is something that remains for a long time. But this is a packet loss due to an instantaneous channel drop. And then after a few milliseconds, it will come back on again. So that will cause TCP to be always in this state, to keep dropping the rate, which is not what we want, okay? Because TCP does not distinguish between congestion and non-congestion, or channel-based packet loss. So we need something to tell TCP whether this is a congestion control or a channel-based packet loss. Okay. That's why the explicit congestion notification can, in a way, solve this problem. Why? Because first we need to have TCP rely on the ECN, or explicit congestion notification control packet from the router, to do any kind of multiplicative decrease. So if one packet is lost or you don't receive the acknowledgement, do not slow down. Okay? But if you receive explicit congestion notification from the next router or one of the router in the end-to-end path, then and only then you decrease. So this is a simple way of distinguishing between the normal congestion-based packet loss and non-congestion-based packet loss. Okay? So that's what we refer to as feedback mechanism. So we need some kind of feedback mechanism. Relying only on acknowledgement is not the proper way, because the acknowledgement may be lost instantaneously from the channel due to some channel behavior that will last maybe for a few milliseconds, but then it will come back on again.
But who return feedback? The receiver or?
No, the router.
We have already ECN. We can send ECN.
Yes.
Yes.
No, that's what I'm talking about here. So ECN is one of the feedback mechanisms. Okay. So ECN when do you send ECN?
Conscious.
When there is congestion. How do you detect congestion? How do you detect congestion?
Queuing.
Queuing. بالضبط. برافو عليك. So this is A. sending to B. In the middle, there is a router. Okay? The router has some queue. We have some packets in this queue. So if this queue starts to fill up quickly, this is an indication to me that that there is actually a congestion. This is not like instantaneous channel behavior now, right? So this is an actual congestion for sure, because if you keep sending more packets and the queue is full, then I'm gonna have to drop, right? So this is an explicit congestion for sure. So the best way is to have the router send this ECN or any other feedback to the source to indicate that this is for sure a congestion. Okay? So TCP needs to change slightly to not rely on acknowledgement for detecting congestion. Okay? Instead, it should rely on some explicit feedback from the network to indicate congestion. When the queue or the queues of some of the routers fill up quickly. That's the only way you can detect congestion accurately. Okay. So this is one problem with TCP, that we can have some explicit feedback from the network to differentiate between congestion and non-congestion packet losses. Another issue is what we call unknown link failure. So we know that the normal behavior of wireless mesh networks or the wireless mesh networks, they have two types of architectures. Remember, we have the infrastructure mesh, where you have heavy routers to form like backbone of the mesh networks, and you have client mesh, or you can have mix between the two. Client meshes relies on the fact that you have clients that are moving like cell phones, and they have ad hoc communication between them, but you don't have an actual backbone or infrastructure mesh nodes to support this communication. Infrastructure mesh nodes are fixed mesh routers that can have some fault tolerance in between these routers. So these routers can use the wireless ad hoc communication to have multiple routes. So if one of these routes go down, then it goes to the other route automatically. So this is what we call fault tolerance. So the problem in wireless mesh network, in the infrastructure mesh architecture, the link failure is somewhat deterministic, or we can have some fault tolerance techniques because the nodes are actually fixed. So we can have, we will not end up with a single point of failure. Like the case of, for example, Wi-Fi with access point. If the access point goes down, then everything is done. Khalas. In mesh network, no. In mesh network, we have multiple routers, and if one of them goes down, I can rely on some other fault tolerance techniques to move around this failure, right? But what is the problem now? The problem happens mainly with mobility. So the wireless channels and the wireless topology in general change with mobility. And mobility here happens with the clients. So clients are mobile. So the link between the clients and the infrastructure routers, this is the one that fails. This is the one that fails with higher probability. Why? Because the client is moving. So the mobility creates large variation in the wireless channel between the client and the mesh routers. So the probability of getting some failures in this link is higher than this link. Because here, inside the backbone, I have some fault tolerance techniques I can, mitigate, or I can work around any failure using fault tolerance, because the nodes are fixed. So due to the wireless channels and mobility, mesh clients, link failures may still happen. So we create, or we at the beginning, we kind of preached wireless mesh network that this is the answer for increasing robustness in the system in comparison to the existing networks, right? The normal wireless networks which rely on access points and stuff, because these types of networks create single point of failure. And we said that, wireless mesh network will resolve this by having, ad hoc communication between the routers and stuff. But the problem is not with the wireless backbone. The problem is with the clients, which are mobile, and I cannot do anything about it. I cannot just fix the clients. They are mobile in nature. So the channel variation between the client and the wireless mesh network router changes and varies, very fast. So, well, for TCP, remember that TCP is a connection-oriented protocol. This is one thing that we didn't talk about in the introduction. What that means is that TCP, before you start any communication, you have to establish a connection. So you have to send a connection request to the receiving entity. And the receiving entity has to send you back an acceptance or a clear message that it can communicate. And then you send an acknowledgement, and then you start communication. This connection-oriented technique is important for TCP to provide some kind of reliability. Because when you establish this virtual connection between A and B, then you can easily create some sequence numbers and know exactly which packet has been dropped. If you don't have this connection, then you have like some packets going back and forth, but you don't know where these packets belong, who this packet belong to, because you do not have proper connection end to end. Okay? So TCP needs to have this connection before it starts to send any data. Which means that upon any link failure, TCP will have very bad performance. Why? Because now we have an end-to-end connection. One of the links is down. So you have to completely disconnect or terminate this connection and re-establish another connection every time. So terminating the connection and establishing another connection is very costly now. It's very costly. Because terminating the connection will take time. And remember, you have some packets waiting in the buffer, so all these packets will wait. There are some packets in the network that belong to the same connection, so all these packets are lost, or alas, they are not delivered. So you have to clear all these buffers, and then you have to re-establish another connection.
And this should be requested from the client.
From the client.
Yeah.
So the client will have to send another connection request, okay, which goes to the network layer or the routing layer, and the routing layer will take this request and say, do I have a route end-to-end to the other entity or not? If the answer is no, then it has to establish a route from the beginning. Okay? So first, you have to disconnect everything that was there before, and re-establish another connection altogether.
This in case of ad hoc or mesh.
In case of everything, in case of anything.
But in case of mesh, we can just move to another route.
True, بس احنا بنقول هنا if there is any link failure. If there is any link failure, which happens a lot, either حتى in the case of mesh, it happens on the client, not necessarily in the backbone, but it happens on the client side because the clients are moving. So the fault tolerance can be done inside the core network or the backbone, but you cannot do anything about the clients. The clients are moving and they create some link failures. So even though the problem is less intensive in mesh networks, but it's there, it's still there. And whenever you have any link failure, TCP will behave in a very funny way. Because you have to disconnect and terminate the entire connection end-to-end and create the entire connection again from scratch. And that will take a very long time. Okay? So, in order to do that gracefully, again, some approaches, they rely on link failure notification. So, because if TCP is not informed about the link failure on time, what will it do? It will not disconnect the connection right away. It will keep retransmitting the packets forever. So, because TCP is reliable, is 100% reliable, right? So link failure will mean that, okay, I will send, I will wait for acknowledgement, I did not receive acknowledgement. Retransmit, send, I did not receive acknowledgement. Retransmit, so I'll keep doing that forever. Okay? So, so one approach to resolve this unknown link failure issue is that I have to inform TCP that there is a link failure. When I inform TCP that there is a link failure, I solve this problem partially, not fully. Because then TCP will say, okay, I will have to disconnect and reconnect. So it will have to go through the process of disconnection and then reconnection again. I would love to do that completely and seamlessly from the network layer without having to inform TCP. I wish I could do that. I wish I could actually detect this at the network layer and transform to another link which works fine and not having to inform TCP. But the problem now is that TCP during this process will keep retransmitting packets forever. So one way to prevent TCP from retransmitting packets unnecessarily is to have this notification or link failure notification to tell TCP, keep in mind that this link is not working somehow, or this is detected from the network layer of the client. The network layer of the client will detect that this link is not working, and then it will inform TCP that this link is not working. So TCP will not retransmit, will gracefully disconnect, terminate the connection, and reconnect again. I wish I could get rid of this disconnection and reconnection again, but at least if I can solve the problem partially by having this link failure notification, that would be nice. So this is another variation of TCP. So through link failure notification. So there is an explicit congestion notification and link failure notification. So far we have two things, and So we need to have explicit congestion notification and link failure notification. So these two were not supported in the default mode of TCP. Okay, and if you can observe, in order to enhance the functionality or in order to enhance the performance of TCP, you have to rely on information from lower layers. You have to rely on information from lower layers, always. And this is what we call cross layers. So in order to optimize the performance of TCP and any protocol for that matter, you need to have, especially over wireless, you need to have cross layer that allows you to get information from the lower layers in order to optimize your performance. So this is a trend in wireless. Any protocol has to rely on cross layers. So layers have to work together, not work independently, like the case of wired. Here, we have to have some interaction, constant interaction between the layers. Why? Because in the case of wireless, the channels are really dynamic and they change a lot. Okay? So you need to have instantaneous information. What's going on underneath? What's going on down there?
Okay.
And that will help you optimize your performance.
Yeah.
Go ahead.
When we can depend in this case on TCP, when we can use it and depend on it.
For the case of wireless, TCP is the predominant protocol. So many people are still using it even for wireless communication.
Yeah, like
Because-
or something like this.
Yes.
Something application layer now.
Oh, application layer. Okay. For application layer,
No, I mean chatting as application layer, but it uses
Right.
TCP.
right.
So
Right.
a lot of applications are using TCP. But
Yes,
I mean,
true. Because it's the predominant protocol, I will not get rid of it altogether. I mean, it's still there. But what we're saying is that it doesn't have the best performance when it comes to applications over wireless. Okay. In order for us to design a protocol that has an optimized performance over wireless, then we need to have some of these variations, explicit feedback mechanisms from the routers to indicate whether there is congestion or not, indication from the network layer of the client to indicate whether there is a link failure or not. Okay, that doesn't mean that if you don't have these, it will not work at all. It will work, but with not the best performance. So these mechanisms will help you to optimize the performance of TCP.
So one question.
So this will allow you to use TCP as is, but have TCP to interpret these explicit notifications from the network or from the network layer and be able to interpret this. That was not originally part of TCP. But these are some incremental enhancements that can enhance the performance of TCP. If they are not there, TCP will still work, but not with the best performance.
So if we have established TCP connection,
Right.
and two routers disconnected for a little time and connected again,
Right,
so
right.
the total connection will terminate.
Well, it depends. If the routers do not notify the client, then TCP doesn't know that there is a link failure. In that case, what TCP will do, it will keep sending the packet,
Okay.
no acknowledgement. This means that the packet was not delivered, retransmit, forever. That's how TCP works. Okay? If the routers or even the network layer of the client, any one of them, detect that there is a link failure and use that mechanism by sending an explicit link failure notification to TCP of the client, then the client will do what? Will gracefully disconnect, okay, and will then try to re-establish another connection. When it tries to re-establish another connection, what will happen?
Everything will start again.
Everything will start again, the request for the connection will go to this router. This router says, okay, this link has a failure. Okay, I will establish another route through this link. It will use fault tolerance in that case. But remember, client is mobile, channel is varying a lot. So you will keep disconnecting, connecting, disconnecting, connecting every time, which will have very bad performance. So I wish I could detect link failure and not having to actually disconnect and connect, disconnect and connect. Okay, but with TCP, this will mitigate, or this will resolve the issue related to unnecessary retransmission. But it will not resolve the issue of having to disconnect and reconnect. Okay? So I solved the problem here, again, partially. Similar to explicit congestion control, or explicit congestion. So we talked about non-congestion based packet loss, and we talked about the link failure or unknown link failure. Okay. Another problem which is also interesting, which happens a lot in wireless, particularly in wireless mesh networks, which is network asymmetry. And what that means is that in mesh networks, it happens a lot that actually this network is symmetric, but it depends on the load on the links. Sometimes when you send a segment, when you send something, okay, it takes a specific delay to go from here to here. But the acknowledgement may in fact go through another route. Or it may go through the same route but takes different behavior in terms of delay. So the amount of delay that the segment takes to go forward is different, or it differs significantly from the delay that it takes to send acknowledgement back. Okay, that's due to a network asymmetry, and that happens a lot in wireless. Why? Because of the states of the channel. Some channels are in a very good state, some channels are in a very bad state. Okay, so it may happen that the segment, while going forward, it experiences relative delay or reasonable delay, but on the way back there is very bad channel fading and so on and so forth. So it takes a much longer time. So network asymmetry is defined as the situation where the forward direction of the network is significantly different from the backward direction, where the acknowledgement usually comes back. So the forward direction and the backward directions are different significantly. Okay. So again, what is the problem here for TCP? Well, as we said, and I hope you appreciate by now, that TCP is very much critically dependent on the acknowledgement in many things, okay, to indicate that there is a packet loss for reliability, to indicate that there is a congestion on the network, right? To estimate the round trip time. Okay, it's critically dependent on this acknowledgement for many things. So if the forward and backward directions vary significantly, then TCP will behave in a very strange way. Okay, so the performance of TCP will be impacted severely by that. Okay.
TCP can be performed on this connection.
Can be
performed. Or
can be optimized, or
it can be established.
It can yeah. In all these cases, it can still work.
On two different routes?
Not two different routes. Even for assume that there is a delayed acknowledgement. Okay, delayed acknowledgement, I still have to calculate round trip time iteratively. The acknowledgement, if it's delayed, that's fine. I will drop the rate. I will still be operational, but not necessarily in the not necessarily use the optimal performance. I'll still work, but not using the best performance.
Okay, but I mean that one connection in the TCP, it can use, for example, ABC routes,
Okay.
and the other direction can use BD.
Could be, yes, yeah, yeah, yes, of course.
Because TCP
Why?
actually is like a pipe. You are creating a pipe, and you're
Yes.
able to send information inside.
Yeah, but the pipe is virtual.
Right.
The pipe is virtual, right? So you could have a forward direction like this and backward direction like this. Okay. So for you, this is the pipe. It's virtual. For you, it's end-to-end path. Okay. But what we're saying is that even if the backward direction follows the same path, you still can have network asymmetry due to the changes in the channel. Because remember, here we're talking about sometimes like multiple radio channels. The channels may not be reciprocal, as they say. So if the channel is not reciprocal, this means that the forward direction is different from the backward direction for this particular channel, for this particular link. So the delay you take to go from here to here is different from the delay you take from here to here. The probability of packet loss on this is different. So you may have a different delay when it comes to sending the acknowledgement. So the assumption here is that for network asymmetry, usually the designers or the developers, they assume that the backward link is much worse. Usually, the backward link is worse compared to the forward link. So the question now is that, given that situation, and given that the acknowledgement is very slow, the acknowledgement is much slower compared to the segment transmission. So how do we optimize the performance of TCP given that situation? Okay. So what happens is that, of course, again, tons of mechanisms have been proposed. Two of them are what we call acknowledgement filtering and acknowledgement congestion control. So the acknowledgement congestion control extends the congestion control technique in the backward direction, which means that congestion control allows TCP to slow down the transmission of the segment on the forward direction, right? So acknowledgement congestion control says, okay, since we have network asymmetry, we will apply the congestion control also at the receiver side to send the acknowledgement back. Because if the acknowledgement takes a long time to reach to the sender, we will slow down the sending of the acknowledgement so that we prevent any congestion on the backward direction. So we'll try to again use the congestion control technique, similar to the forward direction. So again, gradual increase, multiplicative decrease, but for the acknowledgement. So here, the receiver, there is a paper that I posted on Blackboard that explains this. So the receiver here will group all the acknowledgement in the buffer. And then it will send the acknowledgement, and depending on, again, the round trip or the delay that the acknowledgement takes, okay, it may actually drop the rate or increase gradually the rate of sending the acknowledgement. So, because TCP needs to send acknowledgement for each packet, in ideal case, so I can slow down the acknowledgement or increase the transmission, again based on the congestion that happens in some of these nodes on the backward direction. So the idea here again is to use the exact same congestion control mechanism that we used to use for the forward direction to try to use it for the backward direction. So simply when there is any congestion, I need to slow down, which means that the enter delay between one acknowledgement and the other will decrease. When I decrease that, the enter transmission time between two packets, this will slow down the transmission. So basically, if there is congestion, double that time. Okay? If there is no congestion, reduce that time slightly, gradually. Once there is some kind of congestion, then double that time. So that's what happens. The acknowledgement filtering says that instead of using this congestion control on the acknowledgement, I will. So this receiver will have a buffer with all the acknowledgement packets waiting to be transmitted. So congestion control says that I will send this and I will wait for some time, depending on whether there is a congestion or not. Acknowledgement filtering will not do that. Acknowledgement filtering will say, I will go through this buffer. Whenever I find two acknowledgements for the same connection, drop one. Okay? Since there is a congestion on the way back, then I better, because remember the acknowledgement is accumulative, which means that if you send me an acknowledgement that has 1,000, this indicates to me that you have received all the 1,000 bytes correctly. So even if one acknowledgement is lost and the other one tells me 1,000, this means to me that everything else has been received correctly. Okay, so I rely on this notion to say that since the acknowledgement is accumulative, and since this direction is really slow, it doesn't make any sense that I have to send 2 acknowledgements or 3 acknowledgements for the same connection, because one overrides all, right? So it says, okay, so I will go through this buffer. Any acknowledgement that belongs to the same connection, I will drop it, and I will keep only one. Okay? Because if I find one acknowledgement, this is enough. This overrides all. So if I find another one, I will drop it. So this is what we mean by acknowledgement filtering. And that happens because the backward direction is slow, so that will cause the fact that you accumulate acknowledgements in the buffer. If you keep accumulating the acknowledgements in the buffer, then you get to a situation that you have to, if this buffer fills up, you will have to drop, right? So if you drop, now you have to decide, drop which one. Many people, they use the mechanism of drop tail, which means that I have an acknowledgement, I try to put it in the queue. The queue is full. Drop it. But this acknowledgement is very important because this acknowledgement overrides everything in the buffer, right? So it's a much better mechanism to go through the buffer, even if that causes more complexity. Find all the acknowledgement that belongs to the same connection, remove them, and put this one. Are you following this? Yeah. Because the one that I have, this acknowledgement, overrides everything in the buffer. Okay? So acknowledgement filtering.
Question.
Go ahead.
Yeah,
I like the question.
Okay. If you want to replace an acknowledgement, you should remove everything and put the new one.
Well, it depends. I mean, not necessarily everything, but
you can replace particular one.
Yes.
And why it's very costly, as you said?
Because you have to go linear. You have to do a linear search.
Yeah,
Rather than a drop tail is O of 1, right? Talking
algorithms.
algorithms.
Not big.
Drop tail is O of 1. I have 1, I dropped it, right? But filtering requires O of n. I have to go through linearly through the buffer, right?
Yeah, but the acknowledgement is not big, I mean. So you can just see the header and make a condition, I mean.
True, but you have to go through every single acknowledgement, right? But drop tail is, I don't have to do that. I have an acknowledgement, I drop it. That's it. Right, I agree with you. The processing of the acknowledgement is not that expensive, but still I have to do a linear search, okay, which has a worst case of O of n. So still O of 1 is better than O of n. But O of 1 is very, it will affect the performance because this acknowledgement is actually the most important one. So you're removing the most important one and you're leaving less important acknowledgements in the buffer.
Okay, just another question. The acknowledgement filtering is not solving the problem of network asymmetry, just it will not make it more complex.
Yeah, because it will not make it worse because of the fact that you have to drop tail.
Yeah, but it
right?
will not solve the problem of...
It will not speed it up, and no one can speed it up. No one can speed it up. I mean, you cannot go faster than what the network gives you. And even the acknowledgement congestion control, again, it does not make it faster. It just says, I will adapt myself to the congestion of the network. Because if I don't do that, then I end up with a very weird behavior, like drop tailing and so on and so forth. I don't want to get to this, okay? So again, it's trying to work with what you have. It's not, all these are not revolutionary approaches in the sense that they design the whole transport protocol from scratch to be optimized. These are just simple variations to TCP, which enhances the performance of TCP using these simple ideas and simple mechanisms. All what we have talked about now are published or proposed in different papers.
So
But here we're just talking about the main ideas. Go ahead.
Sorry.
Go ahead.
The acknowledgement filtering, it's really like a working solution right now for TCP?
No. These are, again, proposed mechanisms.
Oh, just so
Yeah,
they're
yeah.
not actually using it right now?
No,
Okay.
no.
Another thing, it's halftime. Can I get a 2-minute break? I just need to get some tea so I can concentrate better. If you don't mind.
Okay, let's do that. All right, so these are the variations to try to enhance the performance of TCP. A fourth one is what we call large RTT variations. So RTT is round trip time. Of course, because of the dynamic nature of the wireless channel, the instantaneous measurement for the round trip time in normal cases looks like this. Okay, for wireless it looks like this. Okay, so the variation in the round trip, again, this is because of the dynamic nature of the wireless channel. So this large variation of RTT again affects the performance of TCP. Why? Because TCP relies on the measurements of RTT to calculate the timeout. So if this timeout is not calculated accurately, this will cause what? Premature timeouts. So you can time out prematurely or unnecessarily. Once you time out, the acknowledgement comes. So we want to avoid this situation. We don't want to have very large timeout. Why? Because very large timeouts will waste time. I keep waiting and waiting for no reason. So we need to have a trade-off. We don't want to have very large or premature timeouts. But this is challenging in a situation like this. In a situation like this, even moving average will not help much. So this will degrade the TCP performance because of the normal operation of TCP relies on semi-smooth measurements of RTT. It's not designed for very large variation of RTT like this. So this is a problem, and there's no proposed solution for it. So all the three previous problems, we talked about some enhancement to mitigate or to work around this problem. This problem, I cannot do much about it, or at least there's no specific proposal to fix it. This is actually one of the motivations that we need to probably go into a revolutionary approach.
Yeah, we can write a paper about this.
Go ahead. Be my guest. So I mean, you can try to change the calculation of RTT based on the moving average and things like that. Like moving average is based on linear operation. Maybe you want to make it non-linear or something like this, just to, yeah, you can think about something and you can propose it.
So people haven't already proposed something?
Well, it's not part of the discussion, but I would assume some people have looked at it. So of course, like any other research work, you have to do some survey before you propose something, and then you end up that somebody else on the other side of the planet proposed something, and your work becomes, obsolete. So, as part of this discussion.
But I think it's logical. There is no solution because we change the route completely. So the new RTT will be independent on the other RTT.
حتى even if you change the route, even if you don't change the route, RTT varies, significantly because of the fact that channels keeps going up and down. And
on the same route, it can be smooth. It changes smoothly.
On the same route, and you have channels, with deep fading and channels with good condition and stuff. That still affects it.
But it's still the problem on normal case, not mesh. The mesh
No.
is
No. In normal case, you have wired network. The behavior of the link of the wired link.
Wireless.
In case of one route, wireless.
Yeah.
حتى in case of one route wireless, you still have some variation when it comes to RTT.
It's more variation on mesh because you also change the route. You have variation on same route.
If you change the route, then
the
variation will be much larger. Yes.
Unrelated.
اللي هم ايه بقى اللي
RTT on this route and RTT on the other route, on the new route.
Right. Okay.
So we can't predict RTT. So I think this is the problem. There is no solution.
Well, I mean, still, there is no correlation. You cannot say there was absolutely no correlation, because the new route still uses some links in the old route, right? So chances are there is some overlap between the two routes. So that creates some correlation somehow. So you cannot say they have zero correlation, right? In which case, I mean, you can come up with a solution that can work even for dynamic routing and if the routes change. So, well, if you want to take it from the analysis point of view, I don't think this is tractable easily.
It depends on the network shape. If the network change, all the analysis will be changed.
Yes, all the analysis will change, and of course, this correlation thing is to try to analyze it. Statistically, the correlation between two different routes with some overlap in between. You cannot say that they have no correlation. They still have some correlation, but to quantify or to analyze this correlation is hard. But I mean, you can design a superficial type of mechanism to rely on some nonlinear calculation of RTT which is more accurate compared to linear moving average, and you can come up with a solution and measure the performance and see if it gives you a better performance. And you can do that on NS2. I'm not sure if nobody has thought about that, but that's something that you can think about. So the other category, we'll not discuss it much because it's a whole new category of protocols, and these are new transport protocols. Forget about TCP. So let's take the problem from scratch. What is the best way to design a transport layer protocol for wireless mesh networks? So forget about TCP altogether. Let's design a new protocol from scratch. What is the best way? Well, one thing we have experienced in the previous category of protocols is that we have to rely on information from the lower layers. So layers have to work hand in hand. We cannot be completely independent from the network layer and possibly the data link layer. Okay? So we have to rely on information, and possibly even from the physical layer. Okay? Maybe we can take power into consideration. Maybe we can take collision. Maybe we can take modulation into account. We can take collision, whether the data link layer or the MAC layer has a collision-based protocol or some kind of non-collision based protocol like TDMA or something. Go ahead.
Sorry, maybe this is a silly question, but how many layers are in a network exactly?
Okay, so we have physical layer, we have data link layer or MAC layer. Okay. And we have network layer.
MAC is the data link layer?
Yes.
Okay.
Well, actually MAC is a sub-layer inside the data link layer, but usually we call it MAC layer or data link layer. But they are the same, yeah.
Okay.
If you want to be accurate.
So physical, then MAC.
Physical, then MAC, then network layer, then transport layer. Okay.
In that order.
Yes. Physical is the basement. Okay. Then first floor, data link layer, network layer, and then transport layer, and then application layer. Usually people go with 5 layers. In another reference model, they even divide it into 7. So the network layer is divided into 3 layers, but forget about that. The more common classification is to use 5-layer model.
You said some people use 7?
Well, originally they proposed 7 layers, but later on they kind of combined the top 3 layers into the application layer. Because these layers do not have any networking issues to talk about. The first really real layer that deals with networking issues is the transport layer.
Yeah, but doctor, people who are dealing with the transport layer are only who are configuring routers, right? Not
transport layer. No, routers is network layer.
Yeah.
Routers are network layer. Yes.
But basically, only people who are working on configuring them can access this part.
Which part?
Network layer or transport layer.
Network layer, yes. Transport layer is built into the operating system.
So
transport layer is socket. If you have ever heard about socket,
yeah.
Okay. Transport layer deals with sockets. So when you create a socket, this is nothing but a buffer inside the operating system memory. Okay.
So it's part of the application then.
No.
It communicates with the application.
Configured from the application. It's created.
Well, yes, the application creates the socket. The socket is actually the transport layer buffer, which divides all the messages from the application into segments and put it in that buffer. And then TCP will take it from there. TCP will take the segments inside that buffer and say, I will use flow control to send it with a specific speed. If there is a congestion in the network, I'll slow down, I will increase the speed. And so
So just part of it is communicating with the application.
Right.
No special.
There is an interface between the application and the transport layer. This interface is the socket. So the application sends everything in the socket, and then TCP will pick it up from that socket, and then we'll deal with it.
And the data layer, you said.
Data link layer, yes. Data link layer has to do. It's very much medium dependent. Medium dependent, which means that it differs whether the medium is wireless or wired, and if it's wireless, whether it's Wi-Fi, it's 3G, it's 4G. Yeah, it has to deal with this a lot. It has to take into consideration the characteristics of if it's fiber optics, UTP.
The physical layer is common for all?
No, the physical layer deals with analog signal. Pretty much, يعني. Or at least big part of it deals with analog signals. But it's baseband and RF. It's the RF is completely analog. It deals with like analog signal, whether it's electromagnetic waves or maybe light inside fiber optics and so on.
Okay.
Yeah.
So it's different for every.
Yes, so it's totally different. Totally different. The data link layer is somewhat different, okay, and it deals with the fact that the underneath medium is, if it's wired, then it's designed in a specific way. But if it's wireless, then it's designed in a different way. Okay? But the physical layer is inside that medium. So it's the one that takes care of the signals and encoding and so on.
The frequency channels where the wireless signals are sent is considered which layer?
Physical layer. Physical layer, yes. Power, all this is physical layer. That's why I said that. So the dealing with frequency in terms of allocation is a MAC layer issue. So I want to allocate myself in this channel or that channel or that channel.
Right.
This is a decision that the MAC layer takes. So the MAC layer manages the different channels. Okay? Once you take that decision, you pass this decision to the physical layer to actually create or generate the signal into that frequency domain. So the physical layer will create physically the analog signal in that frequency domain or that frequency domain or that frequency domain.
And this signal is like composed of what exactly?
Analog signal is just analog signal. Electromagnetic signal that gets physically transferred over air or over fiber optics, or fiber optics deals with light, of course, light beams.
Okay.
Yeah, so that's very, very low level. Okay. So we didn't talk about that as part of this course, because we're talking about networking issues. In wireless communication, we talked a little bit about physical layer issues. Again, going back to this, the new transport protocols design a new transport protocol for wireless mesh networks excuse me, from scratch. Okay? So what we have to do now is that we have to, again, the basic thing we have to think about is that the protocol has to reutilize the cross layer, which means that from one node, we have a network. All these links are wireless, right? Which means that if some traffic going from here to here, and some traffic is going from here to here, they will still interfere, which was not the case in wire. So now, this is MAC layer issue. So now, I have to take into consideration that the channel bandwidth in this area, in this whole area, okay, gets divided between those two nodes. So if wireless gives you a channel bandwidth of, let's say, 1 megabits per second, okay, you have to pay attention to the fact that even those two nodes or those two links are not overlapping, but they are still interfering because of the proximity, right? So they still interfere to each other. So when this node sends to here, it also sends to this implicitly, because this is a wireless signal that goes in the air, right? So this node creates some interference on this node. and this node creates some interference on this node. Which means that if these two nodes are sending at the same time, what will happen?
No one will receive.
Collision.
Yeah.
Okay? So why do we say that? We say that because, I mean, what does this have to do with transport layer? Well, it's related because we have to know that the bandwidth of of the channel within this area has to be divided between all the nodes that are going in this within this area, because all these links are interfering with each other. So somehow we need to estimate the channel bandwidth in this area, find which of these links have an actual traffic going on, and divide the bandwidth between them. Right? Try to divide the bandwidth between them. Why? Because they cannot send at the same time. All these nodes, if they have to send something, they will interfere with each other. So we have to divide the bandwidth between them. Right? Do you agree or not? Okay, well,
We will see.
okay. So this is the first step, that unlike wired networks, which is very straightforward, links are going over wire, so you don't have to divide anything. The traffic going on this link will go directly, but they don't interfere with each other. In wireless, however, is much more complicated. This interference creates what we call virtual interference domains, which could be overlapping. Okay? So we have to somehow construct these interference domains, and then estimate the channel bandwidth. Estimating the channel bandwidth may require physical layer information. So you need to know what modulation is being used, you need to know what power is being used, you need to know so many things. Okay? So somehow we can estimate the bandwidth within this area. So the next step, let's divide this bandwidth between all the lengths that have an active transmission, because not necessarily all of them have active transmission. So how do we divide? Well, divide the bandwidth is a MAC layer issue. So now we have to combine physical with MAC layer. Then within MAC, how do we divide the bandwidth? Do we divide equally or unequally?
Okay, it's not clear what does it mean we divide the bandwidth.
We divide the bandwidth again because assume that the bandwidth is 1 megabits per second. Okay, so what if we allow these two nodes to send with 1 megabits per second and these two nodes send with 1 megabits per second? What will happen?
Yeah, the problem here is the
Collision.
interference. Yeah, the collision.
Right.
It's not
So you will
about,
increase collision.
sharing or dividing bandwidth.
Not, but when we divide the bandwidth,
They will not reduce interference.
we reduce the interference. صح? Because we allow them to send independently. Maybe on separate channel,
Yeah.
on separate time, okay, whatever.
You say divide bandwidth, you mean make a different channel.
Yeah.
Maybe on different channels, maybe on different times using CDMA, maybe different codes using CDMA, maybe using collision-based techniques. Okay? But we have to have a division of this band. We cannot afford the fact that we send here with 1 megabits per second and send here with 1 megabits per second. Because what will happen is the actual throughput that you will get is actually very bad because they will keep colliding with each other. You will not get any performance. So we need to have some bandwidth management. Bandwidth management is an clear issue. First, we have to estimate the bandwidth, which is a physical layer issue. Then we have to manage the bandwidth, which is a MAC layer issue. Okay? Then, of course, we need to have a route. And guess what? based on how long the route is, I may need to divide it unequally. Why? Because if I have end-to-end transmission on a longer route and I divide the bandwidth equally, what will happen? The longer route will be at a disadvantage. صح? So I may have to somehow divide this bandwidth proportionally to how long the route end-to-end is. And that's a network issue. Okay? So if I get all this information, at the transport layer, I can then estimate and say, okay, I will send with this rate, which conforms with the longer route, which conforms with my share of bandwidth in each area along the end-to-end route.
But which layer is responsible for calculating the route length?
Network layer.
Which is
Network layer. Using AODV or any dynamic routing protocol. Remember we talked about proactive and reactive. You need to go to back to the material.
Right.
So the route, based on how long the route is, okay, I need to use the length of the route as an indication for me to estimate the share of the bandwidth in each area. Okay? I cannot, it's a combined issue. It's not, I cannot just say use TCP and life will be rosy. No, it doesn't work this way. In wireless, everything is just, it affects each other. So I have to estimate the bandwidth in a specific area from the physical layer. I have to manage this bandwidth from the MAC layer point of view. Then I have to estimate how long the route is from the routing layer, and then in the transport layer protocol say, if I send with this rate, I will conform with everything. See how complicated that is? Of course, combining all these layers in a cross-layer model is just very complicated, extremely complicated, because estimating these interference domains is not easy, because these are overlapping. So this was, by the way, the topic of my PhD and some of the work that Hala has done.
What?
My PhD was about designing a transport protocol in ad hoc network. Yes.
Oh.
So it's just very complicated issue. So you have to rely on combining multiple layers together. It's not, you cannot rely on one single layer. A single layer will not give you good performance at all. But the more layers you combine, the more complicated your algorithm is going to be. So you have to strike some kind of trade-off. And you can use different techniques to estimate the bandwidth, different techniques to manage the bandwidth, and so on. There's no magical solution. So you have to have certain assumptions to simplify how you estimate the bandwidth, how you divide your interference domains, and how you calculate or estimate your share based on the route. Each of these steps has, different mechanisms, and you can, propose some mechanisms to perform this step. There is no magical solution that works for all. Okay, I'm just here explaining the concept, but we'll not go through any specific solution because that's very complicated. It requires the fact that we have to go through optimization techniques and convex optimization and so on and so forth, which is not in our scope. But this is just to give you the idea. The concept is that we cannot, the idea is that if we select the proper rate, for forward direction and for backward direction, and this rate is accurate, then we can resolve many of these problems. Okay? We can resolve the variations of RTT. We don't have to rely on RTT basically for timeouts. We estimate our rate accurately and send with that rate. If the rate changes, I need to estimate the new rate. And I keep doing that iteratively and dynamically. Get some information from physical layer, get some information from the MAC layer, keep going up and down in the layers to estimate what is the best rate at this point in time. And if I can estimate that accurately, I can conform with all the changes that happen in the network. And that would be lovely. However, this is very complicated. Okay? So we'll leave you the floor here.
Well, this is like
Okay.